Hi everyone, today we're going to start with our first unit, which we're technically calling Unit 0, Limits and Continuity. The reason this is Unit 0 is because it is technically an accelerated pre-calc topic that we did not get to last spring. We're going to start by looking at limits, rates of change, and tangent lines. So our two goals today are I can calculate the average velocity and the average rate of change, and I can estimate the instantaneous rate of change at a point. Now, a lot of this information is coming directly from your book, so if you feel like I'm going quickly, you can always refer to that. This section starts on page 59 in your book. But just some background information, rates of change play a role whenever we study a relationship between two changing quantities, and there's a list there of things that you may have seen, one of the most common being velocity. Okay, so for example, if you're driving your car at 65 miles an hour, you can find your position or how far you've driven by multiplying 65 by the number of hours you drive. So velocity times change in time would give you a change of position, which is all fine and dandy as long as you're driving the constant velocity. So the problem of extending this formula accounts for changing velocity. To account for changing velocity lies at the heart of calculus. So there's two different types of calculus. Differential uses the limit concept to define instantaneous velocity. And interval calculus enables us to compute the change in position in terms of instantaneous velocity. So just a little background information there. You're going to see some information in the what is calculus video that you'll see as well. So in this section, we're going to look at velocity and other rates of change, looking at their graphical interpretation in terms of tangent lines. And there's some examples here of tangent lines and non-tangent lines. You probably haven't talked much about tangent lines since geometry. Remember, tangent lines touch the edge of a circle in geometry or a curve in algebra at one point. The ones that are shown here that are not tangent lines, the top three are actually secant lines. They touch at 2 points. The bottom one is neither. But we are going to use tangent lines and secant lines to go back to our velocity conversation. So when we talk about velocity, we want to find average velocity. We're going to calculate the change in position over the change in time. It's very similar to the slope formula. Okay, so we can't define an instantaneous velocity the same way though, because instantaneous velocity has no change in time. So if you divide by 0, it's undefined. So we are going to approximate that using average changes of velocity for values that are closer and closer to the instant that we're looking at. So change in position is called delta S. Delta is what we use to represent change, and that's called the displacement or net change. So we're going to move on. Let's do some examples here. You've seen this before. Galileo's formula for an object falling to Earth under the influence of gravity is S of t equals 4.9 t squared meters. If it is feet, we change that to 16 and kind of go from there. So if a stone is released from a state of rest and it falls to the Earth, estimate the instantaneous velocity at t equals 0.8 seconds. Now, the easiest way to do that is just to test values or find average rates of change that are smaller and smaller and closer to that 0.8. So what I'm going to do is I'm going to find average rate of change from an interval that gets smaller and smaller. So average velocity, average rate of change, average velocity. So what we're going to do is we're going to start by using 0.8 and going to 0.81. So what I'm going to do is I'm going to plug that in and do 4.9 times 0.81 squared minus 4.9 times 0.8 squared over 0.81 minus 0.8. I'm going to plug that into my calculator and I end up getting, and if you type the whole thing and make sure you put parentheses in the numerator and denominator, but I end up getting about, I'm going to say approximately because notation is really important in calculus, 7.889 meters per second. So I'm just going to write that down, 7.889. And we're going to keep going. We're going to make smaller and smaller intervals here. So I'm going to do from 0.8 to 0.805 this time. And I'm going to plug those into my average rate of change formula, and I get about 7.8645. Okay, getting closer to that 8, I'm making a smaller interval. Let's try this one. Okay, when I plug those into my formula down here, I get about 7.8405. So we can see it's about 7.8, but in calculus, we try to go as close into 3 decimal places if possible. So let's do one more. We're going to do 0.8 to 0.80005. We're going to plug that in for our fourth one, which is about 7.8402. Okay, so you'll notice after looking at these, my average velocity on these intervals gets closer and closer to 8.404. I could even go further to make sure it's accurate, but I'm confident in saying that our instantaneous velocity at t equals 8 is 7.840 meters per second. Okay, graphical interpretation of velocity. Okay, we're going to use the secant line, which is really what we just did. We found from here to here to approximate the instantaneous velocity. And as we make sure that is closer and closer to that tangent line, notice we shift these down, we end up getting our answer. So this graph actually represents the curve that we were just talking about. Okay, other rates of change, just pretty basic. Average rate of change formula is the delta f, or the change in the function, is f of x sub 1 minus f of x sub 0 divided by the change at x, or x sub 1 minus x sub 0. Instantaneous rate of change at x equals x sub 0 is the limit of the average rates of change. Okay, so that's exactly what we just did there. We're just going to try to get those intervals smaller and smaller so we get closer and closer to the tangent line. So we are going to go ahead and do one more problem here, and I'm going to try to keep this within 10 minutes, but we're going to do the same thing. If I look at values on the left side and the right side of this formula to approximate, I can just plug these in. So if I look, if we're getting close to 2.73 from the left side, I could start with something like 273. I mean, I could start with 272.5 and go to 273. And I could plug that in our average rate of change formula. I could go from 272.9 to 273. I could go from 272.99 to 273 and test those three values. So if I do 20 times the square root of 273 minus 20 times the square root of 272.5 divided by 0.5, because that's our interval, I get something that is close to 0.6055. Okay. Do the same thing, plug the rest of the values in, I get something that's close to 0.6053. And, nope, that's the wrong one, sorry. 528. So, well, 53 if I round. And then the last one is 0.6052. So that's from the left side. From the right side, I could also go from 273 to 273.01. Or from 273 to 273.1. Okay, and I'm kind of making the intervals bigger. I wrote these backwards. And then 273 to 273.5, for example. Plug those in. We're going to get about 0.6052. We're going to get about 0.6051. and about 0.60 if we round 5. Okay, so to the third decimal place, I am confident in saying that our average is 0.605, our average rate of change. And this is the meters per second per change in, or per Kelvin. That's the rate of change. Okay, so really you're just plugging these into the rate of change formula and testing it out, see if you can get it smaller and smaller, and see what we're getting close to for an instantaneous rate of change. If you have any questions, let me know. Have a great day.